Modern smartphones have become powerful imaging tools, but their compact design forces manufacturers to use simpler lens systems and smaller sensors, which increases susceptibility to noise and reduces image quality. Such limitations are serious concerns in applications like digital zoom. To compensate for hardware limitations, software is used. To mimic optical zoom, for example, image superres is applied, which relies on deep convolutional neural networks trained on large paired datasets. However, collecting high-quality training data is quite challenging. A common approach to obtain data is to capture the same scene with two cameras of varying quality, or the same camera at multiple focal lengths. Such a process, however, is labor-intensive, time-consuming, and requires controlled captures with static scenes and precise alignment to avoid artifacts. Therefore, unprocessing pipelines have been developed to reverse the imaging degradations and camera systems processing steps to generate paired training data. The existing unprocessing pipelines, however, rely on isotropic and anisotropic Gaussian approximations of camera superres kernels, which are not necessarily representative of real-world degradations, and thus introduce a domain gap between real and synthesized RAW. We propose a procedure to thoroughly model superres blur kernels and adopt standardized approaches to model sensor noise for a set of 8 mobile cameras, then use them to unprocess high-res sRGB images into low-res RAW data. Our framework is built on the assumption that, while processing pipelines vary across mobile devices, components such as sensors and lenses may share similarities, leading to comparable degradation profiles. For superres kernel estimation, the overall idea is to use a reference pattern as the latent high-res image, obtain its raw capture observation, and follow the image formation model to estimate the underlying superres kernel. We use a camera and a display setup. We display a high-res color image on the monitor and capture its image using the target camera, and carefully align the known high-res pattern with the raw capture and synthesize the latent high-res image in the camera sensor domain. We use it in the inverse imaging formulation to estimate the superres kernel, which inherently includes the camera PSF and the subsampling operators of the sensor and microlenses. We carefully consider the sensor display geometric mapping and the radiometric difference of the display device and the camera to obtain an accurate alignment. The resulting latent high-res image is used to estimate the 3-channel superres kernels by minimizing a regression loss function. For noise modeling, we use the heteroscedastic Gaussian model. Shot noise and read noise parameters are effectively calibrated using a color chart per sensor color channel. Also, noise depends on the ISO level, so we calibrate noise parameters for a set of ISO levels and fit a spline curve to each parameter to infer the parameters for uncalibrated ISO levels. We first evaluate the accuracy of the proposed kernel modeling approach using 4 different cameras. We synthesize raw data from patches extracted from the diff2k training data and train a superres model with a degradation pool that includes only camera-specific RGB kernels and noise per test camera. The comparison baselines are therefore different only in how they model superres kernels. This figure shows camera-specific superres model assessment on real data captures with 4 different cameras. The 4x superres model trained with our calibrated camera-specific degradations outperforms models trained with the baseline degradation pools, as shown in terms of more detail recovery and fewer artifacts. For quantitative results, we generate raw and RGB paired data using the display prototype and the careful alignment process. We also capture a raw image of the MTF chart to measure MTF25 and MTF50. This table presents quantitative comparisons showing that our proposed degradation framework for camera-specific modeling consistently improves performance across all metrics. We evaluate our model on raw images captured by a Xiaomi Mi11 camera and a Pixel 6 camera, whose superres kernels and noise models are excluded from the degradation pool during training data synthesis to mimic a blind superres case. This figure shows our degradation pool used for training the superres model helps restore more details and generates fewer artifacts compared to other baselines when tested on real data. Note that the 2 test camera degradations are not seen by any of the models during training. For quantitative results, we again use MTF25 and MTF50, along with PSNR and SSIM, showing that our proposed degradation pool consistently improves performance across all metrics. Our results confirm that the test cameras have degradation kernels closer to those in our pool than to the arbitrary random degradations used in other methods, and that our approach reduces the domain gap between synthetic and real RAW, making the superres model capable of better generalizing to similar smartphone sensors.